Hi, welcome to our smartboard. In the earlier example, we looked at flow laminar from a Newtonian liquid along a wall. And the only force was gravity. In today's more complicated example, we're going to take a look at the same type of geometry, flow past the plate, but now there's a real application in mind. Suppose you work in a factory and you have to put a polymer on a film. How do you do that in a process that runs constantly? Because you don't need to make one sheet, you need to make them by the kilometer. Okay, a very simple way of trying and do that is the following. Here is your sheet. You have that, say, on a roll or something, and you have that hanging all in a bath of the viscous polymer, and you pull it out at a certain velocity. Now a little of that liquid will flow with it and coat it. How do you decide how do you manipulate the thickness of this coating? That can be done in the following way. So let me erase this and look at how we could do that. If instead of pulling only the sheet, we would pull it as part of kind of a duct. So this is our sheet, and we're going to move that upwards at a velocity u. And here is a wall sitting still, so it has no velocity. And this is connected to a bath, so liquid can move in. And it will, because there is a drag force upward here at the wall, but obviously there is gravity pulling down. We did this example in this way. Remember from the earlier example. Gravity down and two forces from friction. If this is laminar steady state, we get that the forces sum up to 0, and we're going to note the vertical, the y direction. So this is y, this is x, this is 0, and this is d. The width of the mouth, so to say, through which the liquid can flow is d. If we look further away, so away out of this mouth that stops here, so if I redraw that, but somewhat lower, our film, the plastic, is continuing. And thus the liquid will have to move with it. Here is our sheet that needs to be covered, that moves with velocity u. Alright, liquid was flowing in here because we were pulling it up. Gravity was counteracting, so we need to find out how it flows. But sooner or later it dries up and everything here will flow at a constant velocity. My arrows are too small. Basically, this part is dried up. So let me circle that in yellow. This part is dried up. It has a width delta, the thickness of our coating, and it all moves with the same velocity as the sheet as it's kind of solidified. So the velocity here is also u. Right, if I now set up a mass balance in steady state between these two and I compute for a control volume that runs along this, then in steady state, so a mass balance in steady state reads 0 is in minus out plus a 0 because there's no production, or rephrased, these two must be equal. And thus the flow out here is the same as the flow there. This automatically sets itself to an equilibrium value. How does it do so? By changing this with delta. As much as you get out here, that has to flow there. The outflow is easy. If W is, like we had in the previous example, the thickness of the plate in that direction, then the outflow is W delta times U, the volume, cubic meters per second of product coated on the sheet. And the question is, what is that one? Once we find this, depending on the width of the mouth, gravity pulling down, density of the material, viscosity of our stuff. Those parameters I expect to be in because it's a laminar flow by gravity and a motion upward by friction. If I can equate this in, I can find the rule for my unknown delta and thus understand the thickness. Okay, let's do that. Make a little bit more space. We solved this. That's to say, we backed out that the derivative of the shear stress equals minus rho g. And thus, the derivative, integrating it once, the shear stress itself is minus rho g plus some constant C1 that I give a tilde on top of it. Unknown. In the previous example we had a boundary condition. But now we don't have a boundary condition on top. We have two velocity boundary conditions. So I need to continue and leave this constant in and use that this is Newtonian. So that tau xy equals also minus mu dvy dx. And thus dvy dx equals rho g, there should be an x here, over mu x. I divide by minus mu, so this gets also divided by minus mu, but I can call that a new constant C1 because I don't know what it is anyhow. This can be easily integrated, so Vy equals rho g over mu x squared over 2 plus C1 integrated is C1x plus a new integration constant C2. Okay, two integration constants, two boundary conditions. And I have them, the boundary conditions. At the left part, x equals 0, I have this wall sitting still. The film was on the right side. So Vy equals 0. And thus, if you read these two, that means that C2 equals 0. The other boundary condition is on the other side, on the sheet side. At x equals d, there the velocity of the liquid must equal the velocity of the sheet, and we pull that up with velocity u. If I fill that in, I get that u equals rho g over mu d squared over 2 plus c1 d, and thus I can back out c1, it's u over d minus this one but not d squared. And thus I get my velocity Vx y of x equals c1 times x equals u times x over d, and then these two can be combined. I lose d there, so it is minus rho g 2 mu 1d is gone against that one, and I get an extra x back, so that is dx. And then this part, everything is out, and I took an extra minus sign, so this is minus x squared. Gives me the velocity in this part. So the velocity sitting here at this line. If I compute what that for an inflow gives, I can equate it against what I had here on the top, which contains the delta. So I need to find the flow through that. The volume flow is the integral over the width from 0 to capital D of Vy times W dx. If I integrate this out, I get this is the velocity over the width integrated. So that width comes in front, it's a dummy parameter, and I get u x squared over 2d minus rho g 2 mu. This one gives me dx squared over 2 minus x cubed over 3. And I should all take that between 0 and d, the boundaries of the slit. Alright, move it a little bit down, because I need to simplify this. The lower boundary gives only 0, so I can ignore that. The top boundary gives me the w and then the brackets. X squared, it's going to be d squared divided by d, so it's u d over 2, whereas this is d cubed and a 6. That 6 together with this 2 gives me a 12 mu d cubed. Alright, let's peek at what we had. This is the outflow, the inflow I mean. The outflow was computed slightly higher as W delta U. So now I can equate these two. In was out in this steady state. So this must mean that it's equal to W U times delta, the unknown width. I'll redraw the sketch. The final film thickness delta when you had here a d sitting and this rising with a velocity u. Okay, the w goes out. I can divide one u out to isolate delta. Thus delta equals the u goes out is half d, and I need to subtract minus rho g 12 mu. I need to divide by u, so another u slips here. Then I use from that d cubed d squared here and multiply it by still d. Why? I get a half d of the witness minus a parameter times d. Okay, let's see whether we understand this. If you do this very fast, let me pick a new color so that you can see what I'm trying to do. Trying to test whether this makes any sense. If u is very high, so you do it very fast, then the limiting thickness is delta equals half the width of what we had here. That's the layer that you get if you pull it out very fast, but still in steady state. On the other hand, this can be made arbitrarily big. If I make u smaller and smaller and smaller, I blow up this prefactor. And thus, ultimately, that's going to be larger than a half, and thus delta is going to be negative. No, that can't happen. But it says there's a critical velocity. If this is a half, then nothing comes out. Delta is 0. So if rho g d squared over 12 mu u equals a half, then delta equals 0, no coding at all. You dip it, but nothing can come out. What it actually says is that this is also 0, so there is no net upflow of liquid. And thus I can equate a critical u that I need to have to get anything out. U to that side, the half makes a 6, 1/6 rho g d squared over mu. At this velocity, nothing comes out. Any velocity higher will give you an answer, and there's a thickness. If you make the velocity very high, you will reach half d. And this is actually how people try and steer making films. Note the parameters that you can play with. A little bit with viscosity, the d, density is usually given, this u, but it's not a completely free parameter, because you need also to have production. If you want to maximize production, then automatically you go to half D. So you play with D if you want to have high production. Check this one out. I'll give you the overview. This is not an easy one. Try and do it yourself. Set it on. This is complete analysis. Try this one yourself without peeking and see where you can follow the logic yourself. Good luck.